Okay, so let's talk about even functions first. And so first, I just want to say that this name, this is the same thing as on the handout it says symmetric about the y-axis. You see that? That's the same thing, okay? So what do you think that means to be symmetric about the y-axis? We did this. A flip? A reflection. So do you know a graph that looks like that? Can you think of a graph that is reflective around the y-axis? Parabola, right? It's not all parabolas, but x squared looks like this. Let's see how bad I can draw it. It's if you flipped it around the y-axis, it would look the same, right? So what does that mean? In terms of the algebra, in terms of the function notation, what that means is that if I take an x, so for example here, if I take x is 1, and I take x is minus 1, they get the same y value, right? Because I flipped x from 1 to minus 1, but the y value didn't change, right? They hit the same y value there. Does that make sense? And I can do that with 2 and minus 2. I can do it with any x. So the definition, let me go ahead and put on the next slide. So for all x in its domain, if I take f of minus x, that's in the domain as well, and it's the same y value. So it doesn't matter if I put 2 or minus 2, or if I put 3 and minus 3, the y values will be the same. Okay? And so x squared's an example. Let me write a few other examples. So we said this one. Another example would be absolute value of x. Do you guys know what that graph looks like? Yeah, it's a V. Good. We should have a mime class where you guys only answer with hand gestures. We can do that on Monday for the visitor. All right, so that's another example. I could also just draw one, right? Maybe I could draw a crazy one that I don't know the equation for. Something like this. Right? So we'll look at graphs like that later, but that's even, right? If I can draw better. So you could certainly just make one. All right, so that's even. The other one that we talk about a lot is odd. So an odd function, I don't just mean weird. Another way to write that would be symmetric about the origin. My N has too many loops. That's okay. And so, symmetric about the origin seems like a weird name to me, but I'll show you an example, and I really want to illustrate how this is different than when we talked about inverse functions. Okay, so let me give you an example of one. X cubed is is a great example. Let's put an axis here. So I didn't do a great job there, but you're going to have to bear with me because my artistry is so bad. That's supposed to be y equals x. It's not, but pretend it is. So the key thing is that it's symmetric around the line y equals x, but it's not the same kind of symmetry we did with inverses. When we talked about inverses, we talked about the inverse is the reflection about that line. And this inverse would be cubed root of x, and you could see the reflection. It would be kind of more of a horizontal shape instead of a very vertical shape. Okay? This graph has symmetry about the blue line, or about y equals x. It's not reflective symmetry, it's rotational symmetry. If I took the graph and I spun it like a top, you'd get the same graph again. If I had spun it 180 degrees, okay? Does that make sense? So it's rotational symmetry, not reflective symmetry. And that's the only one we've done that's a rotational symmetry, okay? And so what you can see is, if I did that kind of rotation, if you think about a point up here, again, my axes are way off. Maybe I should just kill the grid. But if you think about a point here, so this is x cubed, 2, 8. The corresponding point down here, do you guys know what it would be? Yeah, -2, -8. Okay, so what that means is we're going to base it just like the even functions. We're going to base it on, hey, if you have f of x and then you want to make x negative, what did he do? He also made the y negative, right? So this is the rule for odd functions. So we can say that f is odd if this is true for all x in its domain. So if you put the negative x, you get the negative y. That's what that rotational symmetry looks like. And then let me just finish this part with a few more examples. So we talked about x cubed. Somewhat trivially, y equals x fits this, right? If you think about just a straight line like that, of course, again, I missed the origin. If 1, 1 is on the graph, then so is -1, -1, right? So that one is also odd, kind of in a really basic way. And x cubed's inverse, y equals cube root of x, that would be another example. So this looks kind of like the horizontal version of that, but it fits the same symmetry.
So you don't always have to look at the graph though, right?
Yeah, there's two ways. One is look at the graph. One is that, let me go back to that slide, is this expression here. If that's true, then it's going to be odd. And you sometimes can do that with algebra where you change all the x's to -x. And then if you can pull all the negatives out so that you get the negative of the original, then you can do it with algebra. And so let me show you how to do that with x cubed. So we'll say f of x equals x cubed. Then f of -x is -x all cubed. What happens when you cube a negative? Yeah, you get the negative again, right? So that would be this, and that's the negative of the original. You see how I got the left and right sides of that definition? I put in -x as the input, and the function became negative the original function.
So I guess what I'm trying to get at is that the exponents, if they're odd, it will always be an odd function.
Not necessarily, because it could have other terms. So let me close this, and I'll show you that on Desmos. But I'll close this video saying that's not always true.